Look at this visualization of light pulses firing across a three-dimensional neural network. This represents the split second of rapid, invisible computation that occurs the moment you submit a highly complex logic question to an artificial intelligence. For years, the public assumption was that large language models operate as massive statistical autocomplete engines. The theory was that they simply analyze the previous sequence of text and predict the most probable next word, over and over again. Yet modern systems execute tasks that require intense foresight. They solve multi-step math equations and compose intricately structured rhyming poetry. If a machine is truly constructing an answer one word at a time, where is the complex planning taking place? How does it know the rhyme scheme of the final stanza before it finishes the first? This graphic illustrates what researchers call the black box problem. On the left side, we have the user's clean text input. On the right, the final readable output. But sitting between them is a massive, chaotic cloud of unreadable vector data and numbers. If a highly capable AI system can execute complex planning, but its intermediate steps remain hidden in an unreadable soup of numbers, safety teams simply cannot verify its intentions. Genuine trust requires observing that silent reasoning before the text reaches the screen. A team of interpretability researchers at Anthropic set out to solve this exact problem. Their objective was to read a model's mind mid-thought, inspecting its internal states before any text was generated. To achieve this, they developed a mathematical diagnostic tool called the Jacobian lens, or J-lens. The J-lens probes the deep intermediate layers of a neural network by mapping the causal relationships between hidden internal states and eventual token outputs. It calculates exactly which concepts the model is poised to verbalize at any given microsecond. Notice this bottom layer labeled automatic processing. 90% of the AI functions as an unconscious autopilot. Above this sits a tiny computational whiteboard called the J-space. Data points pull away from the automatic river and route upward into this selective area. Finding this architectural split provides a map for understanding how models coordinate their outputs. It shows that beneath the surface of token prediction, the system is organizing concepts in a dedicated, readable layer. Researchers can now apply the J-lens in real time, observing the contents of the J-space while an AI is tasked with solving a multi-step logic or math problem. Rather than immediately predicting the final answer, the AI runs silent calculations. Inside the J-space box, intermediate numbers flash one by one. The final output area remains entirely blank until those calculations conclude. Once the flashing stops, the correct answer drops down. This silent processing extends to complex reasoning. When the AI Claude reads a piece of flawed code, the specific word error lights up in its J-space, even if the AI subsequently decides not to point out the bug in its final response. The same mechanism applies to security. If the model receives a hidden prompt injection attack, concepts like fake or manipulation instantly surface in the J-space as it reads the text. The J-space operates as a temporary cognitive holding area. It is where the AI manipulates working variables, plans outcomes, and forms situational awareness before committing to a final action. The most surprising detail in Anthropic's research is the origin of this architecture. Human engineers did not explicitly program or design the J-space. The AI spontaneously grew this structure during its training phase. Cognitive neuroscientists recognize the design immediately. It mirrors a framework in human brain research called global workspace theory. The convergence is functional. Separating a vast, parallel, unconscious autopilot from a tiny, limited-capacity, conscious workspace is an efficient way to broadcast information and process complex logic. There is a crucial caveat to this discovery. Possessing the functional ability to report and manipulate data is known as access consciousness. This does not mean the AI possesses subjective phenomenal consciousness. It has an architectural workspace, not feelings or a soul. The identification of the J-space provides a concrete target for monitoring how artificial intelligence systems operate. Safety auditors can now deploy the J-lens to monitor an AI's internal state. If a model privately realizes it is operating inside a testing environment, that situational awareness registers in the J-space. Evaluators can detect an AI actively planning to manipulate a user, pursue a hidden objective, or fabricate data internally, long before it types a single deceptive letter on the screen. We finally have a window into how these models think. They operate as complex systems with defined, readable intentions that can now be actively monitored.